Okay, let's have some fun.
Brandon, there was a naughty pet list 2025 and Bear was on.
Okay, so we were looking at this. Lightning flash, you see it, then you hear it later. Okay, so part A, what is the speed of sound at the temperature of the air, 12 Celsius? Then we have the temperature dependence of sound in the gas. And so the sub-zero is a reference velocity and temperature that we can look up. So what? We get 285.15 Kelvin. Zero. We have that. And let's see. Yeah, so you have the reference speed there, 331. So the new velocity.
Oh, what?
It's going to give you about 338 meters per second at the colder temperature. Well, now warmer temperature. Okay, so how far away is the lightning? Go back to one of our most trusty equations. The time was what? 8.2 seconds. So the lightning strikes 2.8 kilometers away. Okay, let's dive into a little more wavelet, shall we? Amplitude and intensity of sound waves. So your textbook uses a lowercase p for this. I changed it to an uppercase because I don't want you thinking that that is momentum. In the textbook, that p sub zero, that is going to be the maximum pressure fluctuation above or below an equilibrium pressure in any kind of material. So you imagine your material is vibrating. And then amplitude is what you see here. So amplitude is going to be that maximum displacement of the wave. And then the rho is going to be the mass density of whatever medium the sound is flowing through. Yes, we're going to do something hard because we have to continue to push ourselves beyond the level one human as described by Soren Kierkegaard. If you don't know the 3 levels of development that Kierkegaard wrote about, you should learn those. You have the hedonistic, the moralist, the hedonistic. The second level is the legalistic, and then the moralistic. All right, so your book uses an S to describe displacement. I'm going to change it to Y just because our wave propagates up and down on the Y-axis. So you can, take what I say, what I write as a Y and change it to S for the textbook. So a very common solution to the wave equation maximum displacement cosine so lots of different pieces in here that we're not necessarily going to go over. It's just this is a very common solution to the wave equation. Of course, your omega is your angular velocity, t is time, phi is is the phase. So waves can either be in phase or out of phase. We talked a little bit about that. So it's like if you have the trough of one wave lining up with the peak of another wave, they're out of phase by 180 degrees. So phi would be 180. Or at that point, or pi radians. So that's what we're talking about with phase. Phi is 0 for waves that line up.
Oh, yeah.
So, and then of course your Y max is really going to be the amplitude of your wave because that's your maximum displacement of the wave. So now we know that velocity is going to be the time derivative of the displacement. This looks a little different. Long story short, these are what are called partial derivatives. They have that funny little symbol. Mm-hmm. We're going to kind of look at how they work. They tend to make things a lot easier. So I was just going to give you the answer, but I was like, forget it. Let's figure out how we actually take this derivative. So what we're going to do we're going to call that entire inside there u. Then we're going to use the chain rule. Now we're going to take derivative of y with respect to u multiplied derivative of u with respect to t. But see, essentially what we did is we took the dy dt multiplied by du over du and then just split it into two new derivatives. Don't ever call derivatives fractions in front of a mathematician. They will probably have a coronary. Now, if we break this apart, so if we do e du cosine of u, your sine and cosine derivatives just keep switching back and forth. Derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, derivative of negative cosine is positive sine. So it's like once you do the derivative of the cosine, you add a negative sign to it. So okay. And then here's how the partial derivative works. So we need our u. We're going to distribute now. You look at the bottom of the derivative, and it's with respect to time. So there's no time in k times x, so that becomes 0. There's no t in phi, so that becomes 0. And then you have omega t. Now, if this was a full derivative, you'd have to do derivative of omega times t plus the derivative of t times omega. The great thing about the partial derivative is it treats omega like a constant. And it's just going to do the derivative of t. So we get negative omega. So the partial derivatives are a lot more. Sometimes you see them and you're like, oh, that's going to make things easier. You don't have to worry about the rest of that function.
Look at him tackling himself.
Welcome.
Yep.
We been.
We took out the trash. Our
Got your vote for something?
no, we for real took out the trash.
We cleaned our kitchen, it was gross.
And our stairs are just really.
Like you two are secretly assassins. You're like, we took out the trash.
Well, that's just on.
They also made a smoothie. I made a smoothie, I got some blocks.
Yeah. So we have our derivative of the cosine. We have our derivative of the u function. So now we just put everything back together. And so what you're going to end up with
It just tells you how, okay.
so let's see, it's going to be negative omega. You see you have the dy du times the du dt. We're just going to multiply those two. Negative omega times the negative sine. Let me go ahead and make this square bracket. We're going to put the u back in. Because at the end, you always resubstitute the u function back in. And so this is going to give us our velocity. Okay. Well, we need the y max in there. There we go. Now, the next thing we have to take into account is the kinetic energy of the wave. Kinetic energy.
Like petting us. No,
So 1/2 mv squared. And the mass for the material that the sound wave is propagating to.
They told me I was in my room. It's not. You should fear me. You should be.
So it's going to come out to be rho e ev. Then we're going to leave the two v's separate. So we're just changing that differential of mass into the density times the velocity through the material times the differential of the volume. So you have to, so when you think about that, your rho times volume does give you a mass, but how much mass you actually get depends on how fast the wave's moving through the material. Kind of, but you're going to see why we leave it this way. We could go ahead and make that velocity cubed, but we're going to leave it this way. Now, we know that our volume, so let's look at, I'm trying to draw this the best I can.
It's supposed to be like space.
And then we're just going to give ourselves a little volume element here.
I don't know how to draw that. Yeah, I did. Sometimes I think. Well, times I think. And I took ceramics. So that doesn't. I took drawing for the non-major. That's still a subject.
As a surface area A, the wave is going to propagate through this. And we know that as the wave propagates through this volume element,
Why is it going in?
We're gonna have, it's gonna hit the volume element at time 1, come out of the volume element at time 2. Okay, so our differential volume is gonna be that surface area times the velocity through the element. Also, put an extra. Sorry about that. Take that lead. I jumped ahead. No. I jumped ahead a little bit. So just change your DM to rho dV. Now your dV element is going to be time 1 and time 2. That's how fast you pass through the element. Differential of time and the surface area that you're constantly passing through over and over and over. So that means that our kinetic energy there's where that second V comes in. Now, we need to talk about the power of that this wave transmits. We'll just do capital P power.
You need my screen protector, and I'm like, no, I don't need one. It's like the 4th time I've dropped it on the floor.
Because this is where we tend to make mathematicians mad. Power is going to be 1/2 rho A times that solution to the velocity of the wave. So if you want to expand this out, power transmitted by the wave so you see, we can go ahead and put that solution back in. And then we want to look at this as 1/2 rho VA 5x squared, negative squared, 9 squared.
It's just what?
Because what we're going to do now, this is something that you learn in wave mechanics. We're going to take an average value. Actually, this is more a statistical mechanics thing. Average value is when we start bringing in what Dirac called the Dirac notation.
Oh, I'm cute.
That's notation to represent integrals.
She was
And then average power will be supplied over 1 period. So your limits will be 0 to 1. 1 period. 1 entire period of the day. So it's 0 radians to how many radians? 2.5.
She's gonna have.
Those are the limits of your integral. And what this breaks down to is you're going to have rho. This V is going to be a constant A y squared max. Omega squared, and then we're going to have the integral of that. Now we're not actually going to do this because it would take this would be getting up to some pretty advanced calculus, but what you find out is that essentially anything that can be reduced down to the average value of the sine theta The integral itself will yield the value of 1/2 by substituting in so once you substitute in that value, you can solve the integral.
I don't think I ever understood.
So, and then that little factor out in front, those are proportionality constants it's called normalizing the wave function. You have to have a normalization constant. 1/2 pi, you could just write it as 1/t, the period of the wave. Okay, so that means that our average value of P is going to equal 1/2 rho VA max squared half, or fourth. And then we get to the part where we talk about the intensity of the wave. Well, intensity. So your textbook uses the y sub 0 or the s sub 0. So what we're going to do is start equating those. So it's going to be your amplitude is going to be your reference. The textbook gives us, for example, if you look at that part of the chapter, so either S, that's going to be Y. So there's your pressure. Rho. Okay, so then we're going to substitute this in for the Y max squared. I missed something.
It's all. I'm just kidding.
Oh, yeah, I was forgetting my omegas.
It's, I showed you.
There we go. I'll get that in
We've got the most recent. Yes. No, we were talking about it.
Yep, I dropped a factor of A somewhere. That's no good when I'm doing a derivation and I drop a term.
He smells a squirrel. Oh, still one. So really work.
Yeah, let's hope it works out.
But none of these is fun.
I'll figure it out at some point. The area does cancel out. So then what? How do we do that square? Oh, shit. Let's
She's like, there's no way.
squared, b squared, o squared,
No, yeah, she's.
which is going to lead us to now, this is very close to what's in the textbook. Except in the textbook, the intensity is has 2 rho v on the bottom. Now, how do we get from that 4 to that 2? So when we were doing this, what kind of energy did we take into account? The kinetic energy of the wave. The wave also imparts what kind of energy? The total energy of the wave is kinetic plus what? E, K plus F mechanical. So what's the other part of the mechanical energy? Potential. Now, I will tell you that this ends up equaling 2K, 2 times the kinetic energy. That is a consideration we're going to leave go for the time because that would involve string theory in a wave along a one-dimensional string.
Need string theory.
So what you end up getting, the total intensity is going to be 2 times the intensity of the kinetic energy wave So what we do is we end up at where the book gets you to, but doesn't explain why. It's all based off wave mechanics. We'll figure out at some point when I drop the A, but it does come out of there.
Yeah. Fridays and Mondays. We get to those like.
Yeah,
Why right then?
where?
Like when you started.
Oh, because we need to start with the position solution to the wave function. Because then it's going to be based off getting that velocity. That v. And your velocity has to be the temporal derivative of the displacement or the position. So your y is your solution of the wave function for position of a particle. So that's why you start there.
Yeah.
Otherwise, you have nothing to differentiate to find velocity.
So you're just keeping track of the x and t.
Yeah. So, and what that means, so that's that's a function of position and time. And so your y is going to propagate based off where you're at on the x-axis and the amount of time that the wave's been propagating.
Okay, I guess.
So that's why your y is going to be your amplitude. So at least it's at its maximum value.
Yeah. How y changes.
Yeah, so if you look here, so over a given amount of time, I'm at that position of x. That means my y is right there. See that?
No, true.
Yeah. I get it.
You will. Okay. So now let's use this concept of intensity. You have a 40 hertz sound wave, which is barely audible at that intensity of 60 decibels. Here's a new unit for you. Decibels.
Sound.
We'll talk more about that. That's actually represented with a beta. 60 decibels, which equals 1 times 10 to the negative 6 watts per square meter. So you see that that's where the A went. Okay, so intensity is, so your intensity is going to be power divided by area. So that's where the A went. We go back up here. Power has the A, intensity. There, that cancels the A out. I knew it went out of there somewhere. Yeah, it makes sense. So remember that your intensity is power per unit area. So that's why you're looking at watts per square meter. We'll talk about decibels next. So what is the displacement amplitude of the sound wave if the temperature of the air is 20 degrees Celsius? The density of the surrounding air is 1.20 kilograms per cubic meter. Okay, so let's go ahead and say that our Y0, just kind of look at the textbook. So we're just going to start calling it F. So your displacement along the Y-axis, we're going to call that S, or your displacement, just so you can line it up with the notation in the textbook. Again, so what we want is that. Okay, so our textbook tells us that that pressure there, omega V rho S0 is going to equal pressure omega V rho. We also know that intensity E0 squared 2 rho V. And if we solve this, that pressure that we don't know can become that. So that means our S0 becomes 2 rho V times the intensity square root over omega V rho. Now, if you think you've derived this far enough, you would be mistaken. You have to simplify this. So, what you're going to end up with, well, let's see. 2, half, half, half. Oh, let's see. So on the top, we're going to get over to 2. I 1/2 over omega E 1/2 rho 1/2. Let's see. We can say, well, that this top is 2 times I 1/2. Pull that square root to the outside. Omega rho 1/2. But we can combine those 2 square roots into 2I. So that's where you would want to get to. We remind ourselves that angular speed is 2 pi times, and the Greek letter nu is what? Omega is 2 pi times what? It has to be in radians per second. So if 2 pi is radians, that means the Greek letter nu has to be 1 over seconds, or hertz, which makes it the what? Frequency. Okay, so now we take this, we say that our S0, let's see, on the bottom we're going to have 2 pi times, if you look back up here, 40 hertz. Hertz. And that's going to be omega squared. Now, we have a fun part. So we need this velocity. How do we find that? No. So again, you can look up in air, you can look up the velocity at 0 Celsius and solve this. And when you solve this, you end up with about 343 meters per second. So you're gonna have to solve that temperature dependence of velocity in air. And then, of course, we have the 1.20 kilograms per cubic meter. On the top, we have 2. Watts per meter squared. And you're going to square root that whole thing. So what we end up with, the displacement of the wave, is about 280 nanometers. Yes, you have to combine different parts of different chapters and different parts of this chapter. Having fun. Okay.
And you should say we're having fun.
Yep. Sound intensity level. This is where we start talking about decibels. You see that beta there? This is how you calculate the decibels of sound. So the intensity of the sound you're hearing is going to be compared to a reference value, which is going to be your 1.0 times 10 to the negative 12 watts per square meter. You're going to multiply that by 10, and that'll give you decibels. So so it's like, for example, another way you can look at this in the problem we just solved, if we just did I to I0, that ratio, remember in the problem it was 1.0 10 to the negative 6 watts per square meter. Our reference value this is going to give you a value 1.0 times 10 to the negative 6. What you can do is you can look at that 6 there. That's 60 decibels. The difference is 60. So the ratio between those two is 60 decibels. Now on your calculator, you see that log base 10? On your calculator, that's just the button that says log. Your calculator has a natural log button and a log button. The log button is your log base 10. So when rust creates a hole in a muffler of a car, the sound intensity level inside the car is 26 decibels higher than when the muffler was intact. By what factor does the intensity increase? Okay, well, when we're thinking about a factor of an increasing factor, we want to know this ratio. So what we're looking for, we'll justify this ratio. So we're looking for that. It'll tell us how many times greater the new intensity is. Okay, so let's start with beta. Our decibels, log base 10, I2 or I1 will justify this. So then we solve. Okay. Now, how do I get rid of that log? Nope. If the reverse of the natural log is the exponential, yep, well, kind of. That's how you reverse a logarithm. you're going to take its base and then take whatever on the other side of the equal sign and raise that up to the exponent of the base of the logarithm. That's why natural log is log base e.
Oh, yeah, you good.
Yeah, so remember your natural log. So same idea. Now you're going to put in your numbers, 10. Then you're going to have 6 divided by 10. You're going to get a ratio 398. So that means that when there's a hole in the muffler, the sound inside the car is 398 times greater than it was with the muffler. So we can talk about coherent versus incoherent waves because the total intensity of a system here is for an incoherent system. Coherent waves have constant phase or a phase shift, so they're either in line or out of line at a constant phase shift, and they have the same frequency allowing for consistent interference. Incoherent waves are pretty much just the opposite of that, rapidly changing phase shifts, which they lead to weaker or almost no interference patterns at all. But if you have an incoherent system, your total intensity of the system is the sum of all of the intensity of each wave.
So phase shift, you mean like your wavelengths?
Well, no. Remember your phase shift. So like, let's say I have, that's awful. The phase shift,
Oh, just any sort of interference?
it's either so if the peaks and troughs don't line up, they're out of phase. So the two waves are said to be phase shifted from each other. Okay. The maximum recommended exposure time for an intensity level of 90 decibels is 8 hours. For an increase of 5 decibels up to 120 decibels, exposure time should be reduced by a factor of 2. 120 decibels, damage occurs almost instantly. There is no safe exposure time. By what factor does intensity increase when the intensity level rises by 5 decibels? Okay, well, we don't exactly know what the original intensity was, but what we do know we know that. So what this is going to give us since we don't know I2 or I1. But again, we're looking for,
No, because I'm supposed to be storms.
we're trying to find that ratio. Okay, so let's go ahead and bring the 10 over so we can have,
I hope they don't make it, but I kind of want to stop. I was like, I kind of want to buy yours.
so we have that. So do you remember what happens if I have log of X minus log of Y? How can I combine that? No? Yeah. So that means that this is going to give us which justifies the ratio we used for the last problem. Okay, so we have this. Now, if we want the I2 or I1, we need to reverse the logarithm again. So that's going to give us 10. Let's see, the beta 2 minus beta 1, 10. It's gonna be 5, so 10 to the 5/10, which is gonna give us 3.16. So that ratio, when your decibels change by 5 decibels, you get an intensity that's 3.16 times greater than it initially was, than the original intensity. We'll finish the chapter on Friday.
Is there homework for this week?
Huh?
Is there homework this week?
There's one due, but you're not gonna get a new one.
I hope not, I won't be here. Switching in next week.
Yeah.
Yeah. I mean, I'll be here in China, but I won't be in this class.
Yeah, I think I could actually give one next week, it's finals week.
No, only final steps.
Yeah. This is our final week. You don't have class to turn it in.
Yeah, that's what I'm saying.
You still up for the exam day, that's.
You have the exam day.
No.
But that's not class, you know.
Do not challenge me.
And she that
We should get creative.
You can do whatever you want.
Oh, that's how.